Here is a graph of a function f of x. It is often useful to know the slope of that function for any value of x. The slope of the function is given by the slope of the tangent at that point. A tangent is a line that just touches the curve without crossing it. The slope is different for different values of x, so the slope itself is a function of x. We call this new function the derivative of f of x, and we can write it as f prime of x. So the slope of the curve at x is given by f prime of x. An alternative way to write the derivative is as dy by dx, which we will see later. In many cases, for a particular function f, we can calculate the derivative. This process is called differentiation. One common way to find the derivative is called differentiation from first principles. We will see how to do this in this video. We will illustrate the technique for the specific case of x squared. We will also derive the same result based on a geometric interpretation of the square function. Differentiation from first principles requires us to calculate the tangent of a function as a function of x. How do we do that? We can find the approximate value of the tangent at point P by creating a second point Q, a small distance h further along the x-axis. The line PQ has a slope that is approximately equal to the slope of the curve at P. Point P has an x value of x, so its y value is f of x. Point Q has an x value of x plus h, where h is some small value. Its y value is f of x plus h. The slope of the line is given by delta y over delta x. Delta x, the change in x value between P and Q, is x plus h minus x. This is just h. Of course, we already knew that because Q is a distance h from P along the x-axis. And delta y, the change in y values between P and Q, is f of x plus h minus f of x. So the slope of PQ is delta y over delta x, which is f of x plus h minus f of x, all divided by h. The calculation above is only an approximation of the slope. The problem is that it measures the gradient of the line between P and Q. In fact, P and Q have been deliberately placed quite far apart to make it clear that the slope is not accurate. But what we really want to know is the gradient of the tangent at the point P. One thing we can do is move point Q closer to P. This makes the slope PQ more similar to the tangent at P. The x distance between P and Q is equal to h. If we make h smaller, the points P and Q get closer together, and the slope PQ becomes a more accurate measure of the tangent. In fact, if we make h small enough, the slope PQ can become as accurate as we like. So you might think we could get a completely accurate measure of the tangent by setting h to 0. But we can't do that. If we did, P and Q would be the same point. Delta x and delta y would both be 0, so the slope would be 0 divided by 0, which is undefined. It could be any value. So setting h to 0 would tell us nothing about the slope. What we can do is evaluate the slope as h gets closer and closer to 0. This is called a limit. As h gets closer to 0, the ratio of delta x and delta y often approaches a limiting value. We call this limit dy by dx. Dx represents the value of delta x as h gets infinitesimally small, and dy represents the value of delta y as h gets infinitesimally small. So dy by dx is equal to the limit of delta y over delta x as h tends to 0. This is equal to the slope of the tangent at x, so dy by dx is the derivative of f of x. The previous value we calculated for delta y was f of x plus h minus f of x, and the value for delta x was just h. Substituting these values gives this. This is the derivative of f of x from first principles. We can also write this using prime notation, where we use f prime to represent the derivative of f. So this equation means exactly the same as the previous one. Now this formula doesn't tell us anything specific on its own, because we haven't yet defined what the function f of x is. If we replace f of x with a particular function, we can attempt to find the limit as h tends to 0. This will eliminate h from the equation and gives a formula for the slope that only depends on x. We will use the example of the x squared function and use this formula to find the slope of that curve. To differentiate x squared from first principles, we use the formula from before. We then substitute x squared for f of x. F of x plus h becomes x plus h squared. F of x becomes x squared. We can multiply out x plus h squared. This becomes x squared plus 2xh plus h squared. The x squared term and the minus x squared term cancel out. This leaves 2xh plus h squared over h. We can then cancel out a factor of h on the top and bottom. This gives us 2x plus h. The limit is then quite simple. As h tends to 0, the h term just disappears, leaving 2x. Now the equation no longer depends on h. It tells us the exact slope of the curve as a function of x. So at any point on the x squared curve, the slope is equal to 2x. Here is a table showing the slope of the curve for various values of x, using the formula 2x for the slope. We can verify the formula for the slope by drawing tangents at each point. The table shows the expected slope for integer values of x from -2 to 2. Here is a tangent of slope -4 at x equals -2. It matches the calculated slope for the x squared curve. Here is a tangent of slope -2 at x equals -1. When x is 0, the slope is 0 as expected. Here is a tangent of slope 2 at x equals 1. Here is a tangent of slope 4 at x equals 2. This provides an informal verification that the differential formula appears to be correct. Finally, we will look at a simple geometric interpretation of differentiating x squared. We will use the actual area of the square of side x to illustrate the x squared function. The area of the square, of course, is x squared. Now let's see what happens if we increase the side length of the square by a small amount h. This increases the total area of the square. It adds two orange rectangles to the square, each of size x by h. The total increase in area due to both these rectangles is 2xh. It also adds a small yellow square of side h. This adds an extra area of h squared. So the change in area, delta area, of the square after increasing each side x by a small amount h is 2xh plus h squared. This looks very similar to the earlier formula we derived from first principles. Now let's see what happens if we make h smaller. The two orange rectangles get smaller, but the tiny yellow square gets much smaller much more quickly. As h gets extremely small, the yellow square becomes so small we can ignore it altogether. This removes the term in h squared. The change in area is approximately 2xh, and as h gets smaller, this approximation gets more accurate. So if we look at the rate of change of the area, which is delta area divided by h, we get approximately 2x, and again this approximation gets more accurate as h gets smaller. This is the same result we found previously. This is a different way of looking at the same problem, which hopefully provides an intuitive explanation as to why we can ignore the term in h squared. If you enjoyed this video, please subscribe or visit graphicmaths.com. The link is in the description below.